So let's further drill this in. Let's take one more example now, okay? Because in constraint optimization, the more examples we study, the more rooted we will get in the understanding. So let's take another example. Okay. This time, let's make the example a little bit more challenging. In the sense, let's include multiple inequalities. Okay. So let's take an example. I'm going to take my good old objective function x1 plus x2, okay, and I'm going to give your constraints, two constraints in the following way: x1 squared plus x2 squared is less than 2, x2 greater than equal to 0. So this is like a general problem that comes to you, right? What should be our first step? First step is actually very, very simple. It is called, I would say, standardize the problem. So in standardizing the problem, I need to make sure that remember when we wrote down the expression for a constraint optimization, all the inequalities were what? Greater than equal to 0. So let's convert it into that, because if we don't do it, all our answers will be off by a minus sign. Okay. So standard form. So let's denote this. C1x is the first constraint. Right. So how should I write it? 2 minus, right? 2 minus x1 squared minus x2 squared is greater than equal to 0. C2x is equal to x2. This is already in the standard. So this is my feasible set. Okay. So we can sketch the feasible region quite easily. What is it? The first constraint is saying I should be inside the circle. Oops, there's no undo. Okay, never mind. And the second condition is saying in the plus y plane, right? So, yeah, so that in fact is the right. So this is our quite easy, and the contours of the cost function are anyway like this. So where do you think is the solution? Minus root 2 comma 0, right? So I have my point A. There's another point over here which is also interesting, so let's call it. So this is minus root 2 comma 0. This is root 2 comma 0. So what we'll do is we will look at these conditions which we have just formulated now, and we'll analyze it for both point A and point B and see what is the difference between these two guys. Okay. So let's. So now let's, since we are doing this in the beginning, let's write it down everything explicitly, right? So at points A and B, can we say that the constraints are active? Right? Are both constraints active at point A and point B? Yes. Right? So both constraints are active. Okay. So anyway, that is bookkeeping. Okay. Now for there to be a feasible direction to move in, right? So for there to be a what do I need to happen? I need to have feasibility and a decrease in the function. Those are the two kind of poles, right? So I had grad f transpose, let's call it D. This is less than 0. This gives me what? Decrease of feasibility? Decrease, right? This gives me decrease. And feasibility is going to be given by this. This is going to be feasibility. Quick question, is this second condition like case 1 or case 2 of last time? Case 2, right? Because the constraint is active, right? So let's just write that like case 2. Okay, I'll move to the next page then. Now I want to define the Lagrangian of this problem. So how do I do it? L of x comma lambda. First term should be f of x. Second term, we are just extending what we have learnt to this. So the first term should be lambda 1 c1x, then minus lambda 2 c2x. So if I had n constraints, whether they were equality or inequality, what do? I just keep appending it, right? So you will also find a more compact way of writing this. You will find in many places this is written either like so, lambda I cix, this is one way, and another way is to simply write it as lambda transpose C, okay, where C has all the rows of C are the constraints and lambda is a Lagrangian multiplier vector. Okay, so this is a more compact way of writing it. Now, in order to find what we have just discussed previously, what do I need to do? If I am at, so I want to investigate whether point A or whether point B, how does it look with respect to the condition that we have previously derived. The previously derived condition was grad L equal to 0 and lambda 2 C2 equal to 0, complementarity conditions, right? If those were satisfied, we said that what? It's a candidate, a first order necessary condition for a stationary point. So these are conditions to be evaluated at some given point in the feasible set. These conditions are not going to help you to arrive at a feasible point, that the algorithm will do. But that's why we have taken 2 points for investigation, point A and point B. So at both of these points, let us see what do these conditions say. It should work for point A, it should fail for point B. So let's see, is that actually happening? Okay. So what is our condition once again? So grad with respect to L, x lambda, this should be 0 and what was the statement 1? And lambda, now it will be lambda 1 and lambda 2, both should be greater than equal to 0 because both are inequality constraints, right? So I have lambda 1 greater than equal to 0, lambda 2 greater than equal to 0. This was statement 1. Statement 2 was complementarity. Complementarity would say that lambda 1 C1 equal to 0, lambda 2 C2 equal to 0. This is complement, right? So if you had more constraints, you would just keep expanding so many. If there are n inequality constraints, then you have n complementarity conditions. Okay. So now let's write down a general expression for grad L. What is f of x? What is grad f? We've done this many times. 1, 1. So this guy is 1, 1. Okay, minus lambda 1. What is grad C1? Let's look back at how we defined it. It's minus 2x1 minus 2x2. So that minus can, That minus will make this guy plus, and I have 2x1, 2x2, and then I have a minus lambda 2. What is C2? X2. So its gradient is 0, 1. Okay, the minus sign stays there. So 0, 1. Okay, and I want this to be equal to 0. Right. So if I want this to be equal to 0, does this look like a system of linear equations? Right, in either in x1, x2 or in lambda 1, lambda 2. Right. So this is, maybe I'll just write it here. Okay, so I'm going to get 1 plus lambda 2 lambda 1 x1 and 0, and then I have 1 plus 2 lambda 1 x2 minus lambda 2. This should be equal to 0, 0. Okay. So now let's do this analysis for point A and point B. Okay. So at A and at B. So this is my point A. At point A, where is my grad f pointing? Grad f is always pointing in the same direction, 1, 1. So this is my grad f. Okay. Which way is grad C1 pointing? Grad C1 is the interior of the circle, so it's radially inwards, right? So this is my grad C1. Which way is grad C2 pointing? Upwards, 0, 1, right? So this is my grad C2. Okay. Very good. Now let us let's start peeling these apart. Okay. So at point A, so first we'll just do the intuitive thing. Let us see, is there any intersection giving me a feasible direction to move in? Grad f transpose D should be less than 0. That means I should be to the bottom part away from grad f, right? This region over here. Okay. Grad C1 transpose D should be what? Greater than equal to 0. So that is going to give me which region? Right side, right? It's going to give me this region. So is there any intersection of grad f and grad C1? Yes, currently, which is the fourth quadrant. Fourth quadrant is common. And then comes our second friend, grad C2. Grad C2 transpose D should be greater than equal to 0. That gives me which top half, right? So it gives me this region. Now, is there any intersection? There is no intersection. So, looking at our analysis that we did of the set of feasible directions, we can conclude there is no feasible direction. Now, let us see if the algebra that we wrote over there captures the same thing. Okay. So, here, what was the coordinate? Minus root 2, comma 0. I can substitute this coordinate into the equation that I have over there. So, what does it say? I'm going to get 1 minus 2 root 2 lambda 1 equal to 0, and the second condition is going to give me what? X2 is 0, so I'm left with 1 minus lambda 2 equal to 0, right? I'm just using this condition over here. I substituted the value of x1 comma x2 equal to minus root 2 comma 0, put it into this simple equation, and I solve for lambda 1 lambda 2. So this gives me lambda 1 is equal to 1 by 2 root 2 and lambda 2 equal to 1. Okay, that seems okay. Why? Because the Lagrange multiplier should be positive because it's a inequality. So that seems to be satisfying my statement 1, right? So over here, if I choose these values of lambda 1 and lambda 2, statement 1, right? Statement 1 was this guy over here. Obviously, the way I derived it was by setting grad L equal to 0. That's how I got these values of lambda 1 and lambda 2 in the first place. So I've satisfied that. Lambda 1 greater than equal to 0, yes. Lambda 2 greater than equal to 0, yes. What about the complementarity conditions? It's an active constraint, so C1, C2 are anyway 0, so I don't care, this is automatically satisfied. So you can see that what I very tediously arrived at by drawing half spaces and shading their intersection and all, I can see I'm just, by algebra I'm getting it, right? So this is, I can put a tick mark. This point at minus root 2 comma 0 is giving me a set of legitimate Lagrange multipliers. First order conditions are satisfied. Therefore, as a necessary thing, I can say point A is a satisfies the necessary conditions for being a stationary point. Very good. Now let's hope that this whole thing fails for point B. So at point B, my directions are like so. Draw this over here. Okay. So we are sitting, this is a terrible diagram. To draw the circle first. Okay. And now we are sitting over here at this point. Grad f is 1, 1. This is grad f. Grad C1 radially inwards, pointing towards the circle. This is grad C1. And my grad C2, which was grad C2? 1, 0, comma 1, right? So this guy is pointing over here. This is my grad C2. Okay. So grad f transpose D should be less than equal to, should be less than 0 for improvement. That means I should be somewhere in this region. Okay. Grad C1 transpose D should be greater than equal to 0. That means where should I be? In the left half of this point, right? So I should be here. So there is, so far I am seeing an intersection over here, right? That which is there. In fact, it's an interesting space because it's going to be bounded over here and then like this, right? So it's a different, like a paper folded like that. And grad C2 transpose D greater than equal to 0. Where am I? Top half, right? So that's this region. Is there an intersection? Yes, that intersection actually, if I shade it with yellow, is going to give me, oops, something like this, right? And that makes sense, right? You can imagine that if your algorithm started from point B, for example, I know the solution is A, I need to move towards A, and this cone is giving me a legitimate direction to move towards A, right? So that's what I expect from all this tedious drawing of planes and so on. Now let's see what the algebra does, okay? So what will I get over here when I substitute root 2 comma 0 into this equation? Exactly, so I'm going to get 1 here, just the sign will flip over here. This is going to be the first one and this is going to be the second one. So it implies that lambda 1 is equal to minus 1 by 2 root 2 and lambda 2 equal to 1. Okay. So what has failed us? This guy, first guy has failed us. Right. So now this is a way by which we are translating our geometric intuition into algebra, and the moment I do convert it to algebra, it's easy for me to then code it. Right. So this is my sort of proof that D is not a stationary point. Right. So you notice that this example was really very straightforward, right? It had a very simple objective function. It had two inequalities, and what we did was, and what you should keep in mind as you try to solve problems in the future, first get it into standard form so that the inequalities are all in the way that you are familiar with, greater than equal to 0, right? And your algorithm has given you some points to consider, and at those points we are trying to evaluate whether or not the conditions which we derive hold. The conditions being gradient of the Lagrangian equal to 0 and complementarity conditions, right? So then we basically looked at, we started with the definition of the Lagrangian. As many inequalities and equalities are there, those many Lagrange multipliers get added, That's my big hefty Lagrangian. It looks big, but it's actually very simple. I'm just mechanically adding terms after each other. And I look at these two conditions, and I can see that the conformation between geometry, intersection of half planes, and algebra has given me a proof, right? So what should I say? Should I say A is a stationary point? Strictly speaking, can I say A is a stationary point? If I were being very, very pedantic, I should actually say is a candidate. This problem is very simple. I know A is the stationary point. That's because I drew it and calculated it explicitly. But I should say A is a candidate for a, right? This is nothing fancy. In the world of unconstrained optimization, if I found a point where grad f equal to 0, I didn't say that this is the minima of the problem. Okay, if I define a stationary point as grad f equal to 0, it's a stationary point, but it may be a maxima also. So actually wait, this is a candidate, it is a stationary point, we should say it's a candidate for a minima. Stationary point was simply defined as grad f equal to 0, or in this case grad L equal to 0, so it is a stationary point, but it's a candidate for a minima point. Okay. We will not be doing it in this course, but like we had in the case of unconstrained optimization, first order gave me necessary conditions. Where did I get my sufficient conditions from? Second order. So in constrained optimization also there is a Hessian based sufficient condition. If we get time, we'll go into it. Otherwise, we will work mostly with first order conditions. Okay. Any questions on this? Right. So the next thing that we want to talk about is kind of a opposite step from what I just discussed. What I just discussed was geometry got conformed by algebra. I had some intuition of geometry of intersecting half planes, and I conformed that with algebra. Now, in what we will talk about next, I will show you that there is a problem with this sort of dance between algebra and geometry. Okay, so let's to get this into more formal language, let's define a few things. Okay, these directions that we just computed previously on the example, we call them feasible directions, right?